probably. Well, what I will try to do in this hour or so that we have here is to summarize the research that I have been doing with my colleagues over the last 30 years or so, and restate it in modern cognitive developmental science terms as an integrated framework for interpreting intelligence and intellectual development. So in the talk will have three main sections. In the first section, I will give an outline of what I think is good and what are the weaknesses in the three major fields of psychology which focused on the human mind in its various aspects. I mean cognitive psychology, psychology of individual differences, and development psychology. Then I will summarize a series of studies that we have been doing over the years. Actually, to be fair to my alma mater, which is the Aristotle University of Thessaloniki, where I did most of my academic career. A large part of the studies were done in Greece when I was there, and the most recent studies, of course, were done at the University of Cyprus, where I am since '96. And in the last part of my talk, I will attempt to draw some educational implications of this conceptual framework. I think I have to note that I will not get into the details of the experiments. I will stay at a fairly general theoretical level, and I will present models of the concepts I will be talking about, but provided that everything is published. If you want to have the details, you can just get into the publications that the presentation is based on. And in fact, it's very easy to find everything. If you go under my name in academia.edu, everything that is of importance is uploaded there, so it's very easy to get it. I'm not sure if this is the title that I gave to Christine, but I play with my titles. They all mean the same thing. So these are names of colleagues that have been involved in the research over the years. So let's get to the first part. You all know here that the mind has been the focus of research and theorizing in three major fields in psychology. Classical fields, it's the psychology of individual differences, cognitive psychology, and developmental psychology. And in the last, let's say, 20 years or so, the mind is also the field of cognitive science, which integrates actually the three fields above and other fields as well, such as computer science, linguistics, and so on. Obviously, modern brain science tries to specify the connections between the human mind and the human brain, or the animal brain in general, and the animal mind, if we are allowed to talk in these terms. Artificial intelligence, which tries to build artificial minds, and of course educational science, which is of concern at the School of Psychology, such as here. So let's see what the individual differences psychology was successful at and where it was not so successful. Definitely, differential psychology succeeded to uncover stable dimensions of individual differences, everybody speaks about G or fluid intelligence or crystallized intelligence now. And also a set of abilities such as spatial ability, verbal ability, mathematical ability, and so on. It was extremely successful in the diagnosis of intelligence through tools such as the IQ test. Probably this is the big success of social science, the bigger success in social science. And of course, it has been quite successful in the prediction of school performance in reference to an economic way of diagnosing intellectual ability, such as the IQ test. But it didn't succeed to predict intra-individual variability. There have been attempts to cope with the problem, such as, for example, Gartner's theory of multiple intelligences. But eventually, they didn't offer much so far. For example, I don't think that it's very wise to take Gartner's frames as a source of designing educational interventions, because you may be wasting your time, and because actually the frames are based on other more basic abilities the theory is not dealing with. And also, the theory was not very successful, the individual differences theory was not very successful in specifying cognitive processes. What is underlying G, or fluid intelligence? What is underlying the different domains in terms of the real cognitive processes that do the job, and they enable persons to solve problems and make decisions. And of course, they don't care about development. They never really speak about development. I was telling Christine and Jens in the morning about an interesting paper that I read on the plane that they sent me to review from intelligence. It presents a study that lasted 4 years, and the question of the paper was whether intelligence is stable over the year. So they had 8 waves of testing from 4 to 18 years of age. They found standard things, that the correlation between waves of testing is around 6.6, which is expected, but they also found that 80% of the kids who were classified at the age of 4 to be of low intelligence, that is, having an IQ less than 90, were found at the end, at the age of 18, to be in the top category, having an IQ higher than 120. How is that so? It is because in the way intelligence is evaluated, there is no developmental provision. So if you get a child who spurts low and you compare it in the way the IQ is estimated with his age or her age mates, it's retarded. But when he spurts, he may catch up very quickly. And as a result, he ends up higher. So the lack of a developmental perspective in the theory of individual differences is a major handicap, both theoretically and practically speaking. Cognitive psychology, on the other hand, which has about the same age as differential psychology. They both started at the end of the 19th century, at the beginning of the 20th century, was successful in uncovering mechanisms and processes of learning. They specified, for example, different kinds of mental processes, such as long-term and working memory, and different processes of learning, such as the process of learning Pavlov and Skinner and so on talked about. They mapped they were quite successful in mapping cognitive processes in different fields, such as mathematics and physics and so on. And in a sense, they contributed to the so-called conceptual change movement, which was very popular in the 80s and the 90s. But on the other hand, they didn't eventually go far because they ignored individual differences. Like the differential psychologists, they were indifferent to the developmental dimension and the role of the individual in learning and thinking. It was the other way around in developmental psychology. It may be altered than the other two fields in the sense that the seeds of developmental psychology may be in the work of Charles Darwin. It spurred, developmentally speaking, due to the work of Piaget in the early 20th century. And it was very successful, of course, in uncovering developmental changes throughout the years of the individual, of the development of the individual. They showed us that children or persons of different ages may actually live in different kinds of worlds. The world of the 4-year-old has tremendous qualitative differences from the world of the adolescent and the world of the adult. They were extremely influential in recognizing the constructive role of the individual in his or her own development. And if we turn to the legacy of Vygotsky, they were very successful in revealing the role of society and social influences on the development of the human mind. But they didn't succeed much to uncover learning and processing mechanisms, which was the strong point of the cognitive tradition. They were indifferent, probably because of the approach of Piaget himself to individual differences, and also because both Piaget and Vygotsky and the developmentalists of that period of time were very generalists. They didn't recognize the importance of different domains or the structure of information on cognitive functioning and cognitive development. So we need an integrated theory that would be able to do justice for the architecture of the human mind, to map what abilities exist, what cognitive processes each ability is associated with, and how they are interrelated. Also, this theory has to be able to map the systematic development of the human mind throughout the human life, from birth to the end. It has to have provisions that would enable us to make predictions for individual differences in architecture, in the architecture of the mind and development, to map it on the architecture and development of knowledge, for example, in the development of the human knowledge as is done by the sciences, and of course make provisions for how this knowledge may be useful for education and learning, and even for the clinical, for the needs of individuals who are in need of help. This is my general overview of the architecture of the human mind. On the left, you can see domains. There are not too many, actually. You have essentials and categories, It's based on the recognition and the processing of similarity between objects in the environment. You see space and time. You have numbers and quantities, interactions and causes, ages and persons, and language. So, in more traditional psychometric and cognitive terms, we would speak about categorical thought, spatial thought, quantitative thought, causal thought, social thought, and verbal ability. And each of them is based on a number of co-operators. For example, subitization, which is the ability to automatically, perceptually recognize the numerosity of sets smaller than 4 and do numerical operations within this limit, is present from birth in humans, and we see it in many other animals as well. So, quantitative thought, it starts from there and then differentiates as a result of the interaction with the environment. Also, the perception of causality, for example, the ability, the understanding that my hand is the cause of movement of the glass and this is the cause of movement of the cat, is there as a result of the organization of perceptual information. You do not need to think about it, you just perceive it. So this is, the perception of causality is a co-operator within, for the causal domain, and so on. So there are domains which are somehow the genetic inheritance of the formation of perceptual systems in all animals. Of course, there are other processes as well. So in the center, you see representational capacity, which in standard terms, cognitive psychologists would name short-term storage or working memory and so on. It's the ability to transfer information from the co-processors to representation so that you can deal with according to the needs of the moment and to integrate them. So we go down here where the basic integration process is inference, which comes in different varieties. Since the years of Aristotle, logicians or people talked about inductive thinking and deductive thinking. I don't see the difference that they saw, but I will come back when I will speak about the new study about the inferential system. And here we have hypercognition or consciousness, which is self-awareness, which enables us to monitor ourselves, self-represented, self-regulate, and reflect. So as a result of the interaction, if you see the two-way arrows connecting the various boxes, you can see different aspects of processes cognitive science is dealing with, such as episodic integration, comes from the interaction of co-operator or mental operations in working memory. The interaction between the representational space and consciousness provides executive control. The interaction between the consciousness and inference provides meta representation, which enables us to develop logically. And the interaction between domains and inference gives conceptual change and so on. This is a long discussion, I know that it's debatable, but that's the system which, if we model by structural equation modeling on real data, you can see this structure. In this study, we present an experiment done in Athens and in China, where we tested children from the age of 4 to the age of 7 on working memory tasks, spatial working memory, the COSI task, verbal working memory, real words, and non-words, nonsense words. We tested them on quantitative reasoning tasks. Actually, they were many of the tasks, provided the age of the sample was very similar to the numerical reasoning tasks that we have in the test. So addition, subtraction, things like that. Spatial reasoning, mental rotation, comparison of orientations, and so on. We gave them standard analogical reasoning items like the classification items on 2 dimensions, and standard deductive reasoning items where we control for logical complexity according to the logical formulation of the problem, for example, modus tollens, modus ponens, modus tollens, and so on, this transitivity, this kind of reasoning arguments. And you can see the model, actually. You see that, first of all, there are and we test also for awareness of the cognitive processes involved here. You can ask, how can you test awareness about cognitive processes? A 5-year-old boy or girl. Actually, we show them photographs of kids doing something, 2 photographs of kids doing something. For example, the kid on the one screen is asked to sort out toy cars according to color, and the other kid on the other screen is asked to number them, to count them, the same cars. So the child is asked whether, the child that is tested, is asked whether they do the same thing in their mind when they do their job. And we cross-classify what the 2 heroes are doing. They both classify, they both count, or the one is classifying and the other is counting, and so on. So what is interesting here is that you see that the same factors come at the first order, there and here. We have the spatial and phonological memory. Then we have second order factors, problem solving in the domains, representational capacity, working memory, self-awareness here. We have inference here, inductive and deductive, and we have a general factor in the middle. The top pair of numbers stands for the Greeks. The bottom pair of numbers stands for the Chinese. And the bold digits stand for the model on testing raw correlations. And the italized numbers stand for the model when we partial out H. So you can see that this general architecture stands, and it reminds one of the structure. Actually, we build into the model the equations according to the provisions of this architecture. We run models covering actually the whole age span. We have models that have this form. This is in the younger age phase that we examined 4 to 7, but we have for primary school, secondary school, university students, middle-aged person, and so on. The models always come out very robust. And what about development? Here, this actually was prepared for me by my friend Michael Shire. In our tasks, in the batteries that we use, we very systematically integrate the developmental perspective in the sense that we build in the battery tasks that we know that can be solved by 4-year-olds, 5-year-olds, 8, 10, and so on. So Michael Shire here integrated statistically a study that involved individuals from the age of 4 to the age of 70. Actually here I present a graph involving only persons up to the age of 17. You see here, this is speed of processing. This is working memory. And the green is GF. You see that there is a linear change, almost a linear relation with age of working memory and fluid intelligence, and the expected inverse trade-off between speed and age. One might say that, so they are the same thing, they are very closely related, in a sense, but that's not the whole story. A part of the story is shown here. Here, we separated the individuals in each age group into 3 groups according to working memory. Low working memory subjects, having a performance on the working memory test from 0 to 2 chunks of information. Middle, 2 to 5, and very high, 5 or more. And we have here their fluid intelligence score as a function of age and working memory category, or working memory level. You see that what is interesting is that within each age group, the GF attainment of persons is much closer to their age than to their working memory, which is not what is expected, both from a lot of developmental literature. For example, Pasquale-Leone would argue that there is a linear relationship between working memory development and cognitive development, and he argues that working memory capacity, or in his terms, mental power capacity, starts with 1 at the age of 3, and then it develops by 1 unit every other year, so that it's 1, 2, 3, up to 7 at 3, 5, 7, 9, up to 15 years of age. And it's not what we would expect based on the individual differences in literature. For example, based on papers such as the famous paper, I forgot the name, that has a very catchy title. Intelligence is a little bit more than working memory. That's not the case. So what is the case? What is said there? Kilon, Pato Kilon, that's right, yes, you're right. So what is said there is that it might be the case that within each age level, actually working memory and inference in general, are 2 aspects of the same coin. In a sense, working memory is a measure of the resolution of the representational space, and inference is a measure of the integrative ability available for information in the representational space at a given age. So that's why actually then there is this confusion between working memory and fluid intelligence, because they cannot actually be differentiated. And if you see this kind of picture, you see that you need other information to predict development. Because working memory is a good predictor of individual differences within age groups, but it's not a good predictor of developmental change. I will come back to this to show later that actually development interacts very intricately with these processes. Look at this here. Actually, what we did here is to graph. We tested the model, such as the model that I showed before, for each age phase separately. So 4 to 7, 6 to 8, 9 to 11, 10 to 14, 11 to 15, 12 to 16, 23 to 65. And we tested the models on them, and we got their structural relations from the model. And we graphed them here. So you see that the strength of relation, for example, between working memory and GF varies very systematically. It goes down, up, until to go very up in an output. And this is the relation with between GF and speed. You see that actually they are inverse, because it's either higher than 0, relation between GF and working memory, or low or negative, because it's relation between speed of performance and GF. So the more they move in this direction, the higher they are. So you see that actually they move, they are the inverse, the one of the other. In phases, when there is global cognitive change, that is at the age of 6 to 8, or 11, or at the age of 11, speed rises. And in the phases between, working memory rises. So what I'm saying here is actually develop basic processes measured by indicators such as speed of processing and working memory differentiate in their ability or sensitivity to predict inferential or intelligence development according to developmental phase. In phases of transition, speed is a better indicator because it is a more accurate index of the general condition of the brain and the changes that occur in it. When the change has occurred and we have to rework relations between concepts and build new concepts, then working memory is a better indicator, because building new concepts by integrating previous ones or learning new concepts is by definition working memory hungry. So working memory is a better indicator in phases, let's say, of consolidation of a change that occurred before. Look at this. I'm still working on that, so this may not be the final model. The previous one is published in a recent paper in Intelligence. But this is a longitudinal study where we tested children from 10 to 17 3 times. And here I have the cross-sequential growth modeling of change within inductive reasoning, deductive reasoning, and scientific reasoning. Let me specify. The inductive reasoning component was examined by a Raven-like test that we developed. So we specifically designed the test so that it has 4 levels of difficulty integrated in it. So at level 1, they can work with 1 dimension, like the test that Christine showed me in the morning, like the test we were talking about yesterday. At level 2, they could work on simple two-way Raven-like matrices where two dimensions intersect, for example, such as size and color, or shape and color, and so on. Level 3 involves 3 by 3 matrices where there are between 3 and 6 dimensions to be integrated. And at the final level, there are more dimensions, but there are transformations in them as well. So for example, there are things that change in orientation, change in appearance according to a pattern, and so on. The deductive reasoning test also involves 4 levels. Level 1, modus ponens arguments, very simple arguments that even 4-year-olds can solve. Modus tollens arguments, where there is falsification. The so-called fallacies, affirming the consequent, denying the antecedent, which are items that we know that even many others cannot solve. But they are attainable at around the age of 12 to 13. And at the end, items where you need to have metalogical awareness to solve them. And the scientific reasoning test involved symbol hypothesis formulation, hypothesis testing items. This is the most developmentally based test. Vaguely reminds one of Piagetian kind of isolation of variables and experimental design and things like that. Also for levels, from being able to test a simple hypothesis up to design an experiment with 2 levels interacting, so you have to integrate 4 variables, isolate the one from the other in order to match them with the hypothesis. So, and give me feedback about the title of the paper. The title of the paper is Developmental Bootstrapping in the Inferon. The inferon based on the genome in the following sense. As in the genome there are very basic units, such as the genes that are integrated to give the DNA, which is then expressed into complex organisms and so on. So we have to cease thinking about inductive and deductive reasoning or scientific reasoning as different realms or different kingdoms. They are the same thing. They're just different expressions of the inference, of the integrative process of the mind. So look at here. I'm still trying to refine the model, but look where, and so we have the relations between changes, from 10, 10, 10, 11, and so on, within processes, and we have their interaction. Look here, in this age phase, 10 to 12, for some reason the numbers have been displayed. So it's 10, 11, 12 here, and it's 13, 14, 15, up to 17. Look here that the most important marker of the inferon or the general inferential ability is deductive reasoning. You see that most of the arrows leaving from an ability to another ability leave from deductive reasoning to inductive reasoning and to scientific reasoning. Why is that so? In my view, it's because in this age there is a big change in the ability of the primary school children at the end of primary school to formalize relations and deal with formal relations. And this is extremely useful when they have to deal with problems in the Raven-like kind of test that we have, or in understanding scientific concepts or dealing with them. But then look at, there is a vast empty space here of relations. Why is that? It's because this age, between 12 and 13, everything is changing. So because of the fact that everything is changing, the relations are spoiled. There are cases where the models are not even computable, especially when we have to model deductive reasoning. But then relations are reestablished, but they are changed. After the age of 14, you see you have 13 to 17, then the so-called inductive reasoning, performance on the Raven test, becomes very predictive of deductive reasoning and scientific reasoning. Why is that so? It's because as we move up and strategies for dealing with complexity are acquired and established, this is what is needed to deal with the logical relations in deductive reasoning arguments and to organize experiments in scientific thinking. So that's why in adults, in any case, after middle adolescence, Raven-like kind of tests are so powerful predictors of intelligence. But it doesn't mean that intelligence is just this. So that's the model. Here's something else, which you can do only on longitudinal data. What we do here is it's not very common. Actually, it started by a paper by Tim Salthouse, published quite recently in Psychological Science, where he suggested that if we have longitudinal data, we can take covariances between tests at two different points in time, and then estimate different levels, different models of increasing complexity, and study the change in the covariances between the items. On the assumption that when covariance diminishes, as you add increasing hierarchical levels within the model, you can ascribe the change from one time to another time in the same ability to the hierarchical levels. It's quite complex mathematically to be estimated. It's not unfeasible, but you have to start from the structural equation models and work with covariances between measures of the same ability over time, from time to time. So here, I try to estimate the amount of change in inductive reasoning, deductive reasoning, and scientific reasoning that comes either from G or from G relations across time. You see that from 10 to 12, about 70% of change in inductive reasoning across time comes from G, and about 20 to 25% to 30% comes from across time relations between G factors. But when we get to 12 to 13, this disappears, and all change comes from G. It's the same in scientific reasoning. There is a big difference here, where nothing is computable in deductive reasoning at this age, at the age of 12 to 13. And then the relations are restored. So this is actually another way to see the relations that they are there. There is a strong integrative force that keeps the various aspects of inferential processes together. This changes with age, but this strong binding force is always the source of change in all of them. But deductive reasoning at a single age period, 12 to 13. We still have to decipher why is that so, especially for this ability. Christine, how much time do we have?
About 5 minutes left, and then we'll have some time for questions. If
Okay.
That's okay.
Okay, so let me choose. Here. We have run a number of learning studies. There were learning studies where we attempted to induce change in mathematical reasoning, in spatial reasoning, or in deductive reasoning. Here is an experiment that focuses on deductive reasoning. This involved 3rd and 6th grade primary school children. So 8.5 and 11.5. We tested them on speed of processing, working memory, and reasoning. We involved them in a 4 months experiment where we trained them to become aware of cognitive processes, to acquire some skill in how to activate in the Johnson-Lertz mental models account different mental models that are suitable to test different kinds of logical arguments such as modus ponens, tollens, fallacies, and so on. We train them to spot their strengths and their weaknesses in that, and so on. So it was a training that lasted for a few months, aimed to give them awareness of the inferential processes, give them awareness of their strengths and weaknesses, and provide them facility in inventing and manipulating mental models that would help them solve different kinds of arguments on all 4 levels that I mentioned before. So here we modeled change scores. So we subtracted the pretest scores, we subtracted the pretest scores from the posted scores. And so this is the reasoning game and the awareness game. And we regressed them on speed, working memory, and GF. And they were three experimental groups. We had a control group. It's the first number in each set of 3 numbers. We had let's say, a mild experimental group where there were only 2 sessions that focused only on manipulating argument-relevant mental models, and there was the full experimental group according to what I described before. You can see that for reasoning game, the only predictor was working memory in the full experimental group. For awareness game, working memory again was the only predictor. But here, both groups improved, the limited and the full experimental group. But in awareness, only the full experimental group gained from the training. So in fact, this is an explanation why working memory is such a strong predictor of individual differences in GF. It's because it's highly related to learning the cognitive processes that underlie performance on GF-related tests, inference. And it's more so related with the awareness component of these processes. So the results on mathematical thought are a bit different in the sense that in that case, it's not working memory the best predictor of change, but it's the prior knowledge in mathematics, NGF. And this is because this is a content information-laden domain where prior knowledge is more important than dealing with representations in the representational space. And I'm closing with that. So we didn't have time for the educational implications, so we just rushed. Here is models of the cognitive architecture of abilities at the age of 4 to 7, 7 to 11, and 10 to 16. Look at here. Here, we have a general factor where, which is affected by speed of processing, and working memory and reasoning, quantitative, verbal, and spatial, all belong to the same factor. At the next stage, working memory and GF are differentiated. You need two different factors to account for performance on general or working memory and reasoning. And then, at the age following, in adolescence, they are hierarchized. You have GF at the top, working memory in the middle, and efficiency at the bottom. And I will end up with a little story that comes from my 4-year-old grandson. So, little Andreas was with his other grandparents at their summer house. So when they came to us, I asked him, Andreas, what did you do yesterday? He said, we got into the pool to swim. I asked him, who got into the pool? He said, me. Who else? He said, my mother jumped in. And I kept on pushing him. So who else? He said, my uncle and my mother, my grandmother and my grandfather and so on. Eventually, I kept pushing him and he got the grandmother into the pool. And I knew that this was not possible. So I asked, she's a 95-year-old lady. So I asked him, but did Grandma Urania got into the pool? He said, of course she got into the pool. And I told him, but she doesn't know how to swim. She said, but we taught her. And then I asked, and what did she put on to get into the swimming pool. He said, her swimming costume. What color was that? He said, it was green. So it was a full story. I'm sure you know about these stories. But what does this mean? It shows what is here for this image. That working memory and inference are not differentiated between each other. So they very easily cross the borders. And when they lack information, they fill it in by inference. And when they cannot solve an inference problem, they recall information from memory. It's because there is no awareness of the role of different cognitive processes in the system. This ceases after the age of 7. In which case, they start to build models of how to deal with inference, recall, and so on. And it goes on when they become very accurate after the age in adolescence. Just a single comment. What you see in red there are regions in the brain. So the argument is that the different components of the mental architecture can be associated, or they have been associated by brain research with different parts of the brain. And here, and I'm finishing, is the general suggestion for how education can make use of this model. When we go to representational ability or capacity, we have to train kids to keep things in mind, reiterate, rehearse, think on, recall. For executive control, they have to train to choose, order, ignore, shift between information. When you go to inference, they have to be trained to extrapolate, build analogies, check for validity, check for truth, for consistency, and conclude. And of course, on the left, we have to focus on domain-specific mental operations, such as sorting, relating, differentiating in the categorical domain, counting, estimating, measuring in the quantitative, mapping, focusing, rotating in the spatial, hypothesizing, experimenting, interpreting, theorizing in the causal. And to build learning to learn skills, you have to focus on the consciousness or the hyper-cognitive system and train kids to be able to answer questions. Do I know? What does it look like? Relate with past knowledge. What did I do in the past? Can I try? What new is required? Monitor themselves, observe how it goes, regulate, and so on. And this has to be developmentally sensitive. For example, we have to train dual representation at the age of 3 to 4, logical cohesion at the age of 7 to 8, supposition at the age of 12 to 13, transcendence, inferential transcendence in late adolescence. That's all. Thank you very much.